Super Smash Bros., a fighting game like no other. One of Nintendo's greatest creations, this game has something for everyone, from the casuals to the competitive. Today, we, the students of AP Physics 1 in room F2, will be analyzing the theoretical physics within this amazing game. For this project, we will be using Wait, what the? No, we're not using Melee, we're using Smash 4. What do you... No. Sorry about the mix-up. That wasn't supposed to happen. Anyway, let's get back to the point. Super Smash Bros. Is a video game created and developed by Nintendo, where you and your opponent take control of different characters from various other games and use them to fight to the death. Pretty straightforward. Nothing new, right? No groundbreaking moral changes here. Maybe not, but Super Smash Bros. Is still an extremely unique game. First of all, you don't just hit your opponent until their health reaches 0 when they die. Every hit you land on them raises their percentage value. The higher the percentage, the farther your opponent flies after they are hit. The percentage is directly proportional to distance. The goal of the game is to launch your opponent so far off the screen that they hit what is called the blast zone and die. Another unique feature is how almost every single character in the game, 58 of them, has their own unique moveset of over 20 moves. You have your tilt, grab, and smash moves on the ground, aerials in the air, and specials wherever. Where most other fighting games give you a preset combo like press A, B, triangle, square for a super OP combo, Smash players must make up their own combos. Competitive Smash players tend to get really fancy with their combos, but pulling them off, you need a great deal of knowledge about the game's physics, taking into account percentage, the strength of the move, what direction the move will send the opponent, and the weight of the opponent.
The game plan here with ESAM is, okay, never mind, just completely eliminate your opponent because they're one of the lightest characters into the game with your incredibly strong aerials. Okay, I see you, ESAM.
Ooh, and then the double jump into the dare. You see the
Oh,
green? You see the
baby!
bomb! Oh my gosh!
42 seconds! We don't even get to that point. ESAM!
We should also note that we will be using the in-game weight values as the characters' weights and the official height of the characters for pixel measurements.
First, we'll tap into the physics of falling in this game. There's acceleration downwards in this game as shown with the data on the left. In the real world, if someone would fall from the air, they would speed up until they reach terminal velocity and not accelerate anymore. In the world of Super Smash Bros., an object or character's terminal velocity is achieved quicker than in the real world. The acceleration is negative 20 meters per second squared as shown, with finding the slope of the line going to the terminal velocity. As you can see, in the world of Smash, terminal velocity is reached a lot quicker than the real world. In the real world, it would take about 15 seconds to reach terminal velocity, but in the world of Smash, it would take 0.276 seconds to reach terminal velocity. Ganondorf punches. Next, we will look at the force applied and how it correlates to distance traveled, velocity, and the acceleration of an object that the force is applied on. First, we are analyzing Mario. Mario is punched by Ganondorf at a multiplier of 0%, which means that it is the normal damage that the punch does to anyone. According to the graph, you can see that the velocity of Mario is increasing because there is a force applied. Once the force is applied, you can see that his velocity increases fast, then the increase slows down. This is because once there is a force applied, there is an acceleration according to Newton's second law, which is sigma F equals ma. This acceleration decreases because of air resistance, which is why it decreases per time. You can see this as in the beginning. The acceleration was super high because of the large force exerted. Then as air resistance took in, the acceleration slowed to the point where it's close to 0. With the position graph, you can see that Mario is accelerating due to the curved graph. As Mario is traveling more left, as seen in the video, he is slowing down. You can see that he slowed down because of the fact that at one point, he is not moving in the X direction, but traveling in the Y direction. By looking at the Y position graph, you can see that the acceleration downwards by gravity is non-existent because, as you said in fall speed, terminal velocity is quickly achieved. If we look at the momentum and kinetic energy graphs, you can also see the same thing as you see with the velocity, or that it is decreasing because of air resistance, and also that it increases later because of the force of gravity.
Now let's look into wall collisions with the characters Bowser and Mario. All of the collisions that these two characters endure follow after being Ganondorf punched at 300%. For Bowser, if we look at his momentum versus time graph, we can see that the momentum is not conserved as he flies through the air while constantly colliding into walls throughout his flight. As Bowser keeps hitting these walls, he continuously transfers his kinetic energy into thermal energy through these collisions, explaining why the KE versus time graph shows his kinetic energy slowly decreasing over time. The fact that the kinetic energy decreases over time shows that the velocity must also decrease, since the mass is constant, meaning that Bowser's momentum must constantly change because of the change in speed. This is the same with Mario's collision.
So let's look at uniform circular motion, specifically for a Kirby being backthrown by Mario and another Mario being backthrown by that same Mario. To record the velocities that we got for our data, we simply found the velocity on the same point at different points of time as both Kirby and the second Mario were being spun around in circles before being launched in the air. Just from looking at the velocity and the acceleration graphs, we can tell that the circular motion that was made from spinning the Kirby and Mario in the throwing animation is not uniform at all. This is because in order for there to be uniform circular motion, the objects moving in a circle must spin around at constant speed. The fact that the velocities at a certain point in different times are different and that acceleration is not zero shows that the circular motion is not uniform in terms of speed. Another way we can tell that the circular motion doesn't have constant velocity or speed is to look at the kinetic energy versus time graph of both characters. If Mario and Kirby are thrown around in uniform circular motion, then their kinetic energy versus time graphs would be a straight line, showing that velocity remains constant. However, since both of the characters' graphs go down, this proves that velocity does go down, meaning that the circular motion does not have constant speed. We can also observe the momentum versus time graphs of both Mario and Kirby and see that the graphs gradually go down over time. We know that mass of most characters must remain constant, so what causes the momentum to change must be a change in velocity, further showing that the circular motion for Mario and Kirby is not constant.
How could this happen to me?
Next, we will analyze projectile motion. For Link's partially charged arrows, let's analyze if they follow the fundamentals of projectiles in real life. Judging from that constant slope in the x position versus time graph for the partially charged arrow, we can tell that the arrow travels in a constant speed in a horizontal direction, just like any other projectile in real life. So the arrow follows the real-world physics of projectiles, at least in a horizontal direction. For further confirmation of the following of real-life physics of projectiles in the x direction, we can look at the x velocity versus time graph. If we draw a best line of fit through the entire graph, we can visualize that the line will mostly be linear and straight, showing that the arrow mostly travels in a constant speed in the horizontal direction. Now for the vertical direction. From looking at the y position versus time graph for the partially charged arrow, the slope of the graph continuously changes, demonstrating that the velocity of the arrow in the y direction changes as the arrow travels farther. The velocity of the arrow in the y direction becomes a larger negative value, which is supported by the y velocity versus time graph. So the arrow also follows the real-life principle of how gravity causes projectiles to have a greater negative velocity as time passes. Fully charged Link arrow, which we consider a projectile, if we look in the x position versus time graph, we can tell that it follows the fundamentals of projectiles in real life, because in real life, a projectile would have this shape, as shown in the graph. Also looking at the y direction positions, it would follow the typical projectile where it curves down in its path because of gravity, as shown in the graph. Moving on to the velocity, you can see that in the x direction, the velocity is constant throughout the flight of the arrow, as shown in the x velocity versus time graph. This is just like a regular projectile because in the x direction, there should be no acceleration, maybe just a slight deceleration because of air resistance. If you look at the y velocity versus time graph, you can see that it's just like a real projectile because the velocity increases as it goes down because of the force of gravity that causes the acceleration. This demonstrates that it is just like a typical projectile because projectiles on Earth accelerate downwards because of the force of gravity that applies a downwards force or downwards acceleration, which is causing the arrow to speed up as it travels down.
We created a physical model for the idea of smash attacks. For this model, we used a string, a baseball, a clay ball, a wiffle ball, a ladder, a block of wood, a meter stick, about 2 meters of track, and a wooden replica of Link's Master Sword. First, we tied one end of the string to the sword, then the other end to the ladder so that the sword hangs directly above the block of wood. Next, we laid out the track in front of the wood in the direction that we were going to hit the ball. Finally, we placed one of the balls on the block of wood, pulled the sword back, recorded its height, and released it to hit the ball down the track while recording video. We repeated this with the same height and different balls to emulate a smash attack hitting different characters of different weights. Next, we increased height to emulate charged smash attacks. Finally, we plugged the videos into Logger Pro to analyze them. The results were nothing unusual. Less mass and more force resulted in higher acceleration, velocity, and speed.
We make a couple of mistakes throughout the project. Many of our graphs could have been much more accurate if we had used a capture card for more precise video footage, or if we had used Logger Pro with more care than we did. But we did, however, gain a large section of the data to analyze for the project. We also could have managed our time better than we have. Instead of spending all the time on collecting data, we should have started to make the film so that we do not have to cram.
Hi,